Hello, my name is Christopher Arthur, and I'm a math tutor at Collin College at the Plano campus. And today I would like to talk about Markov chains with random walks as choreography. So in particular, what I would like to show you is an example of applying the Markov chain as a way to decide something to do with dancing. So I'd like to show you some dance where the Markov chain sort of influences the way that the dancer moves. And I have a video I'd like to show, but before we get to that, I want to say a few things about the theory behind the Markov chain. So let's start with Markov chains. A Markov chain is a probability calculation, and it involves sequential changes among a limited number of states. And the probabilities of those states sort of take the form of a matrix. So for example, here I have a 3 by 3 matrix. And so the rows and the columns sort of represent the changes between the present and future states, in our case where the dancer might be. So let's look at that in a little more detail. So let's say you have 3 different states or 3 different positions, and you want to know what was the probability of going from the second state to the third state. Well, then you would look at the second row and the third column, and what you would see there is a number that represents the probability of that transition. And so when you have a series of transitions, you got to start somewhere, and we call that the initial state. And the probabilities for the initial state we can represent with a vector we call the initial state vector. And for our case, with 3 states, we have 3 coordinates in that vector, and we could label them x, y, and z, where you would suppose that x is a probability of starting at the first state, y would be for the second state, and z would be for the third state. And if you would like to know, for instance, what are the probabilities associated with the states of the second step after the initial one, you could take your initial state vector and multiply it by the transition matrix, and you will get a second vector that represents the probabilities for the next step. All right. So let's talk about graph theory for a little bit. So here's a graph, and it has points and lines, and basically the lines are like arrows that direct from one point to another. And if you have a graph like this, one way that you can represent it in terms of a matrix is something that we call an adjacency matrix. And the adjacency matrix has ones and zeros, depending on where you find the edges between the vertices. So for instance, here, in this case, we have a 1 in this matrix in the second row and the third column, and that corresponds to an edge that goes from the second vertex to the third vertex. All right. So what we would like to do is make use of this adjacency matrix as a transition matrix in terms of a Markov chain. But the problem is that generally it's not going to fall into the right requirement, because the transition matrix is a probability distribution, and that's going to require that the rows sum up to 1, whereas in the case of our adjacency matrix is not likely the case, so we have to transform it. And the way that you can transform the adjacency matrix is simply to add up all the numbers in one row and then divide each of them by the total. So like here we have 1 and 1 in the top row, and if we divide them both by 2, then they both become halves. And you can do that on a row by row basis and transform the entire matrix into something that will work as a transition matrix. All right, so for instance, then how would we make use of that, to try to come up with a Markov chain for a graph? Well, let's say that we're going to start moving around on the graph in some random sort of way, and we can begin with an initial state vector that has a 1 in the first coordinate, and that says we're going to be 100% certain that we're going to start at the first vertex. So we put zeros as probabilities for all the other vertices. And then if you look at the calculation here, we multiply the state vector by the transition matrix, and we get a vector for the next state. And what it is saying is that there's a 50-50 chance of ending up at vertex 1 or vertex 2 if you didn't know better where you're going. And if we look back at the graph, we'll see why that is the case. So looking at vertex 1, you see that there are actually 2 outgoing edges, one that goes to 2 and then one that goes back in the circle back to 1. And so that's why those are the only two possibilities, and we get zeros for arriving at the other vertices. That's not possible. And you could continue this calculation and get a likelihood for the next step after the second one. And in this case, we can see that you get a probability of 1/4 pertaining to the first 4 vertices, and the 5th vertice is still unreachable. And that kind of goes with the picture again. If you look, if we started at 1 and we tried to get to 5, we would have to take 1, 2, 3, 4 steps. So there's no way to get to it by just 3 steps. So that's why it's a 0. But it would change to a positive number if you would take that and multiply it by the transition matrix one more time. And so a random walk then is essentially, well, it's essentially making use of this idea of probability as it pertains to making decisions about which way to go on a graph, and assuming that you have choices to make, given that you will walk along the edges of the graph, then, you know, making it random says, I don't know better what's going to come next. I don't know what next step I'm going to take, or much less the step after that. But I do sort of know that it's all going to happen within the framework of the graph that is laid out before me. Okay, so let's talk about choreography. So basically, for the sake of what we're doing, I think of choreography as like a set of different dance movements. And what's significant about a given set of movements is that in some cases, these moves can follow each other. And in other cases, maybe they cannot, because one requires a setup where another one doesn't quite end up in that same place. And so what we can do is say that a dancer can follow a sort of network graph where two movements would have an edge between them if one can immediately follow the other one. And so you think of the dance moves as vertices and the connection between them as edges. All right, so, you know, what you can do for the sake of training, you know, like a dancer can sort of go through the motions of different movements and without having to know which one's coming next. If you would like to develop some kind of fluency to know which moves connect well to others. And so what we do is we kind of get the computer to make up random sequences following the graph that we laid out. And so in my case, I chose Capoeira, which is a Brazilian African dance fighting style. And here is the graph that I made that corresponds to the way that all the moves that I know sort of relate to one another. So you can see there's one in the middle that sort of relates to everything, almost everything, and then there are others which relate to each other in different ways. And the vertices have numbers, and those numbers correspond to different movements. And I made a list of all the names of the movements, and I didn't bother to put the names on the graph because I thought, well, there's not really enough room for them to see. So once I made the graph, I told the computer to call it a Markov process, and then I asked it to do 5,000 random walks, each of length 30. And so after I had 5,000 random walks of length 30, I then told the computer to pick the best 26. And by the best, I mean the ones with the most variety. Because when you have a completely random walk, you can't necessarily rule out the possibility that the computer is going to tell you to do the same 2 moves back and forth 15 times or something like that. And you know, that would be really tedious for a dancer. So we look for the ones that have the most variety. I have 34 different moves, and I would like to try to get most of them into any random walk that I would perform. Okay, so let's talk about the video. The video is going to come up in a minute. You're going to see this graph on the page, and then on the other side of it, there's going to be a picture of me dancing. And you can follow along and see every time I make a move, the graph is going to change a little bit. It's going to be like, you can see how I'm walking along the graph by doing different maneuvers one after another. Okay, so that's about all I have to say, and I'm going to put the video on in a minute. And thank you for listening. And if you have any questions, I think you can find me at the Math Lab also. All right, goodbye.
Ginga, queixada, ao reversão, ginga, queda de 4, rolê, dual batido, ginga, parafuso, ginga, ao pra frente, macaco reversão, ginga, queda de rins, negativa, S dobrado, ginga, queda de rins, ginga, ao batido, negativa, roleio cabeça, negativa, ao, ginga,